Hello, this is the phase one explanation for the final project done by Manoj Sunkara, Bayav Liang, and then Sachin Subramanya Bhatt. As explained in our final project proposal, the goals for this week are exploring how to disable a node traffic reconfiguration and self-healing network on each node and graph traversal. As depicted in the final presentation, are to emulate a IoT network that we would like to use our device in. We are going to have a fully connected network topology as depicted here. However, a software-defined network will be sitting on top of it, which would actually make the nodes not see all the possible links allowed and then just use one to two links per node and route the packets according to the shortest path. And this was the experiment created in Data Lab to illustrate this. We have four nodes and each node is interconnected with the other node. And we use this because our net FPGA is capable of containing four interfaces at a time. In order to use all four interfaces of the net FPGA, we came up with this number and this topology. So upon getting this topology, we manually calculated the shortest path algorithm, manually traversed the shortest path algorithm, and then updated the routing table of each nodes to make sure that we get the software defined network that's depicted on the right. So in this case, if we want to send data from node 1 to node 1 will transfer the data to node 0, which will in turn forward it to node 3, and then that goes to node 4. To illustrate this, we can look at all the routing tables, which are updated accordingly. The four terminals are logged into four nodes, node 0, node 1, node 2, and node 3. Let's look at the routing tables. So all the four routing tables were updated by the software to make sure that we have the network depicted in the shown earlier. To make sure that we are able to ping all nodes, let's ping the rest of the nodes. So node 0 can ping all the remaining nodes. Node 1 can also ping all the remaining nodes. Similarly, node 2 and node 3 can also ping all the remaining nodes. So this illustrates an example of all the full connectivity despite disabling of links by the software. The pseudocode for the next process would be explained by Priya.
So here I present to you a pseudocode representation of what our team is trying to do. So as Manoj just showed you, the routing table of each node actually contains the IP addresses of all the rest of the nodes. So meaning that there is a physical link that exists between all of the nodes, but in our but this project is the self-healing portion of this project is going to force the nodes to ping the other nodes based on availability. So even though their actual routing table would have the IP addresses of all of the nodes, just because the software can tell them that one particular node is corrupted, and to avoid that node, they can just be pinging other nodes instead to reach their final destination. And here I'm going to explain how that routine works. So we have outgoing packet and incoming packet routines for the node. We're going to focus on the incoming packet routine. So if the node receives a message telling that you are corrupted, so this node that's executing this routine is corrupted, then it's going to execute subroutine 2, which is basically takes itself away from the network and just check itself. And when it's ready to ping its neighbors, telling them that it has recovered and should be included back into the network. And then if say that we are the neighbor node of a corrupted node, we examine our incoming buffer and we see that this node is corrupted. Then we tell the corrupted node that you're corrupted. And then we go to the subroutine 1, which is telling my neighbor that this source node is corrupted, and we update the table. And notice that once we tell the corrupted node that they're corrupted, this outgoing packet would then evoke this line in that corrupted node. So they would execute subroutine 2. And following that, if I'm the neighbor of the corrupted node, I would then execute this line to exclude the corrupted node from my routing table, and then keep telling my neighbors that of that node that is corrupted. Eventually, this should stop when all of the nodes are notified in the network, which is just not shown in the pseudocode, but we do have that in mind. And instead, when we are not telling the other nodes that one node is corrupted, but when it's ready to be included again, we update our table saying that that node is up and running again, and do similar to this line and just notify the rest of the nodes in the network that that node is up again. And when we update table, if we see that it is a corrupted node, we can just mark it as unavailable in the routing table. But that entry still exists in the routing table. We just find another way to ping it, such as go through another neighbor, go through the other side to see if that side can have a way of reaching my actual destination. But that's gonna be the focus of next week. And here is just making the recovered neighbor available in the routing table again and notify the rest of the network. We're now aware that there is another way of doing this on Feature Lab, and our teammate Sachin is looking into that method. But this is what we have currently in mind, and we will go through this route to see which approach is more feasible at the end and just adapt that. I also want to mention that even though right now it looks like it's like a very software-oriented routine, it does have the potential of make use of the, like, it does have the potential to be turned into a hardware accelerator. If we just say have like what we did in class in the IDS, and just mark all of the paths with like a valid bit and just marking that invalid, and then through like combinational logic we can just find what is the IP address that we should ping if we want to go to source node X. But we will explore that in the next week. This is our progress so far.
So like Bea explained, our teammate is looking into the how to do the corrupted node this thing. So one of the major ways that we are looking into it is by pooling. So each node will be pooling and inspecting all the packets in the background to see if it receives a packet that indicates its neighbor is corrupted. So our teammate is looking into writing scripts that do the pooling and get into work. So we'll be demonstrating that or any other path that we have of decided to implement in the next week. Thank you.